Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics Section Pusat Pengajian Pendidikan Jarak Jauh Universiti Sains Malaysia. This is course JIF 318 Quantum Mechanics. We are in chapter 6 on the solutions of three-dimensional time-independent Schrödinger equation. This is segment unit 6.3 on angular momentum of a particle. The objective of this segment is basically for you to be able to describe the three-dimensional angular momentum of a particle. So how well you can measure the angular momentum of a particle? The particle, in order that it to be measurable, the particle must be in an eigenstate of each component of operator L. Okay, operator L. That is operator, also its component, operator Lx, component Ly, and Lz. However, this is possible only if the components, operator Lx, component y, and z all commute with each other. But that means basically it is when you commute it, it equal to 0. As an example, let us check whether Lx and Ly commute with each other. Okay, so we have this commutator of Lx and Ly, and basically the definition of Lx is from here in the green box in matrix form. For momentum, it is equal to operator R multiply or cross product operator P, and the cross product you can spread it out into a matrix form. The first row is the direction of the axis ijk. Second row is the operator of position xyz, and the third row is the operator for momentum px, py, and pz. So if you here basically is the definition for Lx. That means if we look at the matrix here, Lx is basically ypz ypz minus zpy, and the definition for Ly is actually xpz. Sorry, this is Ly here. Sorry. Xpz minus zp, but for the second term here for Ly, actually there is a negative sign in front, so now we have the zpx become positive and xpz become negative. Okay, to simplify the expression, we need to know all commutators of the form pzx, pyz, and so on and so forth. That means we need to determine the commutators for the other relationship between momentum and position operators. We call that commutator for one-dimensional momentum and position operators. We have discussed previously. If we have position vector x and commute with momentum vector also in the x in the same component, it is equal to I h bar. Here same component, that means the same axis. Here x, the momentum also in the x-axis. And similarly for the y and z component, that means if we have z here, we have pz here, is equal to I h bar. If we have y here, we have py here, again, we should get I h bar. If the position and momentum correspond to different component, that means, for example, like here, x and py. That means different component, and it should be equal to 0. That means as long as they are in different component, y pz, maybe z px, z py, all those will give you 0 values. Okay, so these two properties you should memorize. That means if the position vector and the momentum vector, position operators and the momentum operators are in the same component, that means referring to the same axis, then the value should be I, the commutator should be I h bar. But if they are from different component, the commutator should be 0. In general, we can represent it with this equation. We have position vector alpha, P, that means momentum vector beta equal to high H bar delta alpha beta, where x, y, and z correspond to alpha equal to 1, 2, 3, and beta equal to 1, 2, 3, 2. And the delta here, delta subscript alpha beta, is called the Kronecker delta. It has the value of delta alpha beta equal to 1 if alpha equal to beta. It is equal to 0 if alpha is not equal to beta. That means here it is the same component, that means referring to the same axis, and here referring to different component or different axis. So we have to memorize this in the sense that whatever position operators multiplied by momentum operators, if they are from the same component or referring to the same component, it should be equal to I h bar. If the commutator refers to different components, then it should be 0. Furthermore, the different components of position and momentum all commute with each other. This was also discussed previously. This is, for example, position vectors commute with position vectors. If they are from the different component, the commutator of position vectors from different component, it should be equal to 0. And also, in this second one is the momentum operators. If they are from different component, should also be equal to 0. So more or less, the rule of thumb is if the position vectors or the position operators and the momentum operators, and also in this case you can see here the commutator of position and momentum operators from different component. There are trees. Okay, here we have commutator of position vectors. Here we have commutator of momentum operators. Here we have commutator of position and momentum operators. If they are from different components, that means referring to different axes, it should be equal to 0. Okay. And we also might requires the use of identities. And this is also discussed in the previous lectures. For example, if we have a commutator of summation of AB and also with C, operator C, then it is like we multiply by parts or commute by parts. First, commutator of AC, and here positive sign plus, then commutator of B and C. Okay, and if it is commutator of product of AB and C, then again we can more or less see here that first commutator of C and B, yeah, B and C, then commutator of A and C. Okay, so if we commute B and C, then the A should be at outside of the commutator sign before commutator of BC. But if we commute A and C, then B should be outside of the commutator sign, except that now it is after the commutator signs. Okay, so let us check the commutator of Lx and Ly. That's mean from different component, whether the commutator is 0 or whatever. Okay, so again we refer back to the matrix just now. Lx is equal to ypz minus zpy, ly zpx minus xpz. Okay, these identities allows the equation to be reduced to using the previous identity here. For example, the first one, we can get this. Here I write here, you try this out. Okay, please try this out. Okay, these identities allows the equation to be reduced to, so Lx Ly equal to ypz, commutator of ypz, zpx, and so on and so forth here. The second and third terms are 0 since they contain only factors which commute with each other. Okay, this one and this one, the second and third term is equal to 0 when we commute it. Okay. Okay. As they contain only factors which commute with each other. So when two operators commute, basically it is equal to 0. Hence, what is left is this. Okay. Then again, we commute this first term and second term. You can see here that you have 4 operators in each one. Then we can rearrange basically, okay, so that we have this solution. Finally, the solution is that for different component of angular momentum operator, it is equal to IH bar multiplied by the operator of Z. Okay, that means here X and Y, and the result will give you the operator of along the Z axis. So similarly, for the other operators Ly, Lz, if we have Y and Z here, we have X, Z and X, we have Y, so on and so forth. Okay. None of the 3 components of the angular momentum of a particle commutes with any of the others. So they are not commute in the sense that it's not equal to 0. You can see here that it has some finite values. Okay, it's not equal to 0, so it does not commute with any of the others, with each other. So that means we cannot measure the full angular momentum exactly. Okay, we can measure only a single component of the angular momentum. That means we can measure single component Lz, Lx, Ly. We can measure, but for the whole angular momentum, we cannot measure it. That means the full angular momentum. The question: can we measure anything else apart from angular momentum, or the total angular momentum, or the components? The component we can measure. The total angular momentum we cannot measure. Can we measure anything else? We can measure the square of the magnitude of the angular momentum. Or okay, the square. For example, like here, the corresponding operator is operator L squared equal to Lx squared plus Ly squared plus Lz squared. This one we can measure. This operator commute with Lz. because the operator L squared commute with Lz. Okay, Lz is a convenient choice as in spherical coordinate. Remember that when we want to use spherical coordinate, usually it refers to z-axis, while x and y are silenced. They are replaced by angle phi and angle theta. Okay, but z-axis is still there. So the angular variables are usually measured relative to z-axis. So we want to check whether L squared commutes with Lz. As the statement here says that this operator commutes with Lz. So from here, we expand L squared to Lx squared plus Ly squared plus Lz squared. Okay. And then using the identities, so we have these three commutators. The first one is Lx squared with Lz. The second one Ly squared with Lz. The third one Lz squared with Lz. Okay. The last term is 0. This one is 0 because it is from the same component. Okay. This is the identity which I use. The other terms gave, so we are left with Lx squared, commutator Lx squared and Lz, commutator Ly squared with Lz. Okay. Then we use the identities here. Lx squared, for example, is actually Lx multiplied by Lx. So we can say the first Lx as A, the second Lx as B. So we can use this identity to get this. Okay. And we have the commutator of Lx, Lz, and so on and so forth. This one is equal to Ly. This one equal to Ly, Lx, yes. And the commutator of y and z will give you Lx. The commutator of Ly and Lz will give you Lx. And finally, it's equal to 0. So you can see that the commutator of L squared with Lz is equal to 0. This means that a particle can be an eigenstate of L squared and Lz simultaneously at the same time. Okay, if the L squared and Lz commutes, that means the particle can be an eigenstate. That means it has a state of Lz and L squared simultaneously at the same time. So the conclusion is that we cannot measure the full 3D angular momentum of a particle exactly. And in addition to that, you know that we have proof that the square of the total angular momentum operator, that means L squared, commutes with Lz. Okay, which that means if they commute, then the particle can be in the eigenstate of L squared and Lz simultaneously. Simultaneously means at the same time. At an instant, the particle can be in eigenstate of L squared and Lz. Thank you very much for your attention.